Faraday's law of electromagnetic induction is a fundamental principle in electromagnetism, discovered by Michael Faraday in 1831. It describes how a changing magnetic field induces an electromotive force, EMF, in a conductor. This principle is the foundation for many electrical devices, such as transformers, electric generators, and inductors. Statement of Faraday's law: the magnitude of the induced EMF, E, in a circuit is directly proportional to the rate of change of magnetic flux, phi b, through the circuit. E equals minus d phi b divided by dt, where 1. E, induced EMF, in volts. 2. Phi b magnetic flux, in Weber, Wb. 3. T, time, in seconds. The negative sign represents due to Lenz's law, which states that the induced EMF opposes the change in magnetic flux that causes it. Magnetic flux, phi b. Magnetic flux is a measure of the quantity of the magnetic field passing through a given area. It is given by phi b equals pa cos theta, where 1. B, magnetic field strength, in Tesla, T. 2. A, area of the loop, in square meters, m2. 3. Theta, angle between the magnetic field and the normal to the loop. Faraday's law: for a coil of n turns, for a coil with multiple turns, the induced EMF is proportional to the number of turns, n and n. E equals minus n multiplied by d phi b and divide by dt. Applications of Faraday's law: 1. Electric generators, mechanical motion. Rotating a coil in a magnetic field induces an EMF to generate electricity. 2. Transformers. Changing magnetic flux in the primary coil induces an EMF in the secondary coil, enabling voltage conversion. 3. Inductive sensors. Detect motion or position using changing magnetic flux. 4. Electric motors. Induced EMF affects motor performance, back EMF. 5. Magnetic induction cooking. Alternating current generates a changing magnetic field, inducing currents in the cookware for heating. Lenz's law complements Faraday's law by determining the direction of the induced EMF. It states: 1. The induced EMF produces a current whose magnetic field opposes the change in the original magnetic flux. This ensures conservation of energy. Demonstration of Faraday's law: 1. Moving a magnet near a coil. Moving a bar magnet into or out of a coil induces a voltage. 2. Rotating a coil in a magnetic field. A rotating loop in a uniform magnetic field produces alternating current, AC. Practical considerations: 1. Eddy currents. Undesirable induced currents in conductive materials can cause energy losses. Mitigation: use laminated cores in transformers. 2. Rate of change. Faster changes in magnetic flux induce a larger EMF. 3. Material properties. Conductivity and permeability of the medium influence the induced EMF. Faraday's law is a cornerstone of electromagnetic theory and underpins modern electrical and electronic systems. It explains how mechanical energy is converted into electrical energy and vice versa. Next topic on renewable and non-renewable energy. Thank you for watching. Like, share and subscribe.